everybody. How was class last week? Yeah? Felt like it was pretty solid. Ms. Katoon is pretty awesome. And I think a number of you maybe had her before, so that always helps. So we're going to build off what she did on Wednesday of last week. So Wednesday of last week, she kind of set us up with some of the numerical calculations. She said that most of the people in this class felt relatively comfortable with some of the calculations that were semester 1 calculations, so calculating molarity, molality, those kinds of things. So we're going to build on that today. But once again, one of the most important factors in this class is to reflect. If this is something that it seems like everyone in the room knows how to do and I don't know how to do, make a note of that and then make sure to come meet with me or your friends or figure out how to address those, okay? So our first question, we have 16 responses. So I have two structures up there. Which one of these is more polar? And then the second part of the question is what I really want you to discuss in your tables. What experimental evidence would you be able to gather, you as expert scientists, be able to gather that would confirm or refute your answers? So go ahead and take about a minute, talk to your tables, and try to figure out what you would really want to be able to see experimentally to confirm this. Try to be as far apart as possible.
These are normal.
What do you all do with this? What's your experimental? Okay. How would that help? Okay, so make sure we use the same term. So in harder to break, if we're talking about boiling, we're talking about two of these separating from each other. So by breaking, we say we're breaking the molecule there, which we're not doing during boiling. So just be really clear on how we refer to those terms. Okay, what other ideas? Okay, so how do we test that? Alright, so let's hear some ideas. Can I get volunteers? How would we test which one of these is a more polar compound?
See, based on the intermolecular forces, A has a hydrogen bonding, so we have a higher and B more polar.
Okay, so as far as the theoretical side of things, I absolutely agree. So we look at these two molecules, we see that one of them is capable of dipole-dipole interactions. In fact, the strongest of them, hydrogen bonding. So between two molecules of isopropanol A, we would be able to have hydrogen bonding. B, what's the strongest intermolecular force between two molecules of octane? London dispersion. There's no polar bonds. So even though there's hydrogens, remember those hydrogens are not part of a polar bond, so they will not be any part of a dipole. So London dispersion forces can't exist. Okay, so then the question is, what experimental evidence, what could we do that we could measure and determine which one of these is actually more polar to substantiate that claim that A is a more polar molecule? Say again?
Boil them.
Boil them, why?
Because the one with the weaker intermolecular forces boil faster.
Boil it at a lower temperature or with less heat added? Yeah. Great. What else could we do?
Freeze it.
We could try freezing, same type of principle, and the one that freezes at a lower temperature has weaker intermolecular forces. What else? What did we start talking about on Wednesday that's relevant to this?
Pressure?
So there's something we talked maybe a little bit about vapor pressure. We could measure how much gas is above the liquid at any temperature, and that vapor pressure would tell us something about it as well. What did you talk about in class on Wednesday? Solubility. So how does that relate to answering this question?
See if there's any sort of like partial reaction. I don't know if that's not the word I'm looking for, but
So what is the word we're looking for? Anyone help out?
Partially charged, or partially negative, partially positive.
So based on partially negative, partially positive, there's going to be something to do with solubility, solutions. mix it into what type of solution? So what polar solution do we know of? Does everyone know of? Water. Okay, so let's take a big beaker of water, and let's pour, in one of the beakers we're going to pour isopropanol. The second beaker of water we're going to pour octane. What do you expect to see visually happen with those two? Is there going to be any difference? Talk amongst your group. What would you expect to see that would be different if you poured those two molecules into two different beakers of water? And why? Which one will? Would A would dissolve, you're thinking? Would B dissolve as well? So I'm going to ask for a response from this group in about 30 seconds. So think of your group response.
I put A, because I was just thinking the hydrogen bond.
Because the eyes get to carbon, there's no.
And can I ask everyone to keep bringing your name tags? Because I'll admit that I'm terrible and I have not remembered everyone's names yet. Okay, can I hear from this group?
Okay.
What would you expect to see differently when you poured those two compounds into two different beakers of water?
Well, the A, I guess, is partially polar, so it might dissolve a little bit, because like dissolves like.
Does everyone remember that term, that phrase? You've all heard that, like dissolves like? This is what it's talking about.
And then whereas B is completely nonpolar because of the CH bond, so they're not going to mix, kind of like oil and water, I guess.
So it's CH and CC bonds. That's all that exists in this molecule here. So what would it look like when you say it mixes a little bit or it doesn't mix?
Well, B wouldn't mix at all.
So what would that look like?
Yeah.
You'd have separate layers. So you'd have, you've seen when you have olive oil and water, forms two different layers or forms droplets. Olive oil actually does dissolve a little bit, which is why you add it to pasta. It's actually a colligative property, so we'll talk about that in a little bit. It's kind of cool. Or adding salt. Either one of those are not done for what you think they're done.
What's the like dissolve like in the
So if you have a polar solvent, this one will dissolve at least to some extent, if not a significant extent. So actually, the numeric value you can measure that if you have 1 liter of water at room temperature, you can dissolve 1,000 milligrams or 1 gram of isopropanol in water. It'll completely dissolve. If you add more than a gram of isopropanol, then you'll get a separate layer that forms. So because this has polar bonds, it is more polar overall. That is going to dissolve up to a certain amount. This one is not polar, so polar and nonpolar will not dissolve each other. So like dissolves like means if they're similar in polarity, if they both have partial positive charges, partial negative charges, or if you have an ion, then that's going to dissolve in something that's polar. But if you had a container of octane and you put sodium chloride in there, will it dissolve? Put sodium chloride into a container of octane, is that going to dissolve? So sodium chloride, would that dissolve in octane? Why or why not? What type of partial or full charges exist in sodium chloride? Full positive, full negative. So yes, they're going to be able to dissolve if the solvent has at least partial positives and negatives. So we can dissolve sodium chloride in water. We know that. We can dissolve a lot of it before it gets saturated. But it's not going to dissolve at all. So if you have gasoline, which is, we basically say that gasoline is octane. It has a number of other things too that are similar. But if you poured table salt into your gasoline, it's just going to go right to the bottom. It's not going to dissolve at all. However, if you put sodium chloride into isopropanol, it's going to dissolve a little bit because they're a little bit similar. And water is much more polar, so it's going to dissolve more well in water. The more polar the solution is, or the solvent is, the more you would have a salt dissolve in that. So let's look at these two then, the next two on your sheet. Like the other one?
Both of them actually.
Talk amongst your table to figure out why you answer one or the other. Or either. I don't know.
So, wouldn't, the positive charge on the carbon, partial positive charge on the carbon, would be spread out over all.
So if you have a bond here, then you can have that charge. But here is a source of partial positive. Alright, everyone have their answer in? We got 20 clicks. Feeling pretty confident here? Closing out. So let's have, from this table here, can someone share out of your discussion of which one you might have chosen and why, or some of the debate you had?
We were stuck between B and C because there's still one polar bond in A and B, but we didn't know.
What?
There's like the O and the C.
Okay.
Oxygen, carbon.
Are there any other polar bonds in this molecule?
O and H.
O and the H.
That one too.
So forget when they're shown
Well, they have
together.
the same number. So each of them both have two polar bonds. So we didn't know if the amount of non-polar bonds canceled out like how polar that whole molecule is, or if they're like the same because they both have two polar bonds.
What do you think? Does anyone argue very strongly one side or the other?
We did not agree with that.
Okay, so what did you say?
Well, we said A is going to weigh less, the atom, because there's,
The molecule.
the molecule. So it's less weight, and then the dipole is more localized in one direction.
On one side of the molecule, you mean? Okay, so based off of that, which one do you think is more polar?
We said A.
Okay, should we look at the clicker responses? So distributed, but about just over half the class, almost 2/3 of the class said A, and I agree. And there's a couple of different reasons. So the discussion that your group had is exactly right.
I said the wrong letter, by the way.
I didn't even remember which one you said at the end, if you said B or A, or you said B and C.
Yeah,
I think were the
and
two you're looking
meant
at. A and C?
other one,
Yeah, okay, fair enough. So the major take-home points about this is, what is the strongest type of intermolecular force that can occur between two of these molecules? And in this case, it's hydrogen bonding, because you have a highly electronegative oxygen, highly electropositive hydrogen that form a dipole. But if you were to take both of them and put them into water, you would find a very significant difference in their water solubility. And the reason is, the way to think about it is the ratio. How much of the molecule is polar? How much of the molecule is not polar? And so you said that there's this, like, part of the molecule is polar, but then the rest of it's kind of separate. And so the way I think about it, I don't necessarily need you to count individual bonds, but if there are the same number of polar bonds, which is what your group said, but then there's many more nonpolar bonds, then the nonpolar bonds are not only going to make it way more, make it harder to get up to speed, have more dispersion forces, but they also repel water. So that left side of molecule B over Mia does not dissolve well in water. And so you've probably seen in your biology classes lipids, lipid molecules are an exaggeration of this. So if we were going to do a blank screen, that's a terrible blank screen. Let's do GraphPad instead. So a lipid is going to have a polar head group that's actually even more polar than the alcohol that we just saw. So it's going to have this kind of a polar group at one end. So not only has OH, but a carbon and oxygen connected there. And then it has a long carbon-hydrogen chain, something like this. So that's a typical lipid, is it has that polar group at the top. It has a very non-polar group down here. And so that polar group dissolves very well in water. The other end does not. There's even more polar versions of it that have something attached here, like acetyl-CoA, that actually have a charge. They have an ion attached there. And so that makes it even more water-soluble. So I agree with that while they look like they might have similar abilities to hydrogen bond with each other, that extra added greasy part, or the carbon and hydrogen, is going to have a big impact. What about these two? 30 seconds. More seconds.
So,
5 seconds. And closing out.
I'm thinking too critically now.
All right, who wants to argue their case? Class is split. No noticeable trends here. Kevin, you want to share your group's discussion? Why? Why'd you choose C? So they have the same number of nonpolar bonds, not only the same number, but literally the exact same of each type of bond. Same CH bonds, same CC bonds, and what else? Same polar bonds, same OH and carbon and oxygen. So I concur. If we were to go measure this experimentally, we might find a little bit of a difference because of the three-dimensional representation in water, that some of them stack a little bit better than others. But as far as their water solubility, they're almost identical to each other. So from my standpoint, what I really want you to think about is there a high ratio of polar to nonpolar bonds, in which case the molecule overall is going to be more water soluble. If there's a lower ratio, if there's many more nonpolar bonds than polar bonds, it's going to be less and less and less water soluble or less polar.
So the way it's drawn or the way it's shaped, it doesn't matter.
The three-dimensional representation of them does have an impact, but minimal compared to having a lot more of additional types of bonds. Does that make sense? Is that fair? Okay. So those are the types of things that I want you thinking about from polarity and which is more or less polar. So on the exam, you can definitely count on having questions like that, where we have multiple molecules. I heard last class there was a little bit of confusion when she showed a whole bunch of morphine derivatives and trying to figure out which one's more or less polar. So absolutely go back and look at that set of questions from last class and now see with the kind of ratio we talked about if it's easier to answer those questions. They're very complex. But if you look at the core, you can see that they're actually almost identical except for just a couple of tweaks, a couple different bonds. So are we taking away a nonpolar bond, putting a polar bond? Are we taking away a medium polar and putting a high polar? Those kinds of things are what I want you thinking about. So today in class, we're going to spend time digging into calculations. So I want you to be able to calculate the change in boiling point and freezing point, which you have practiced in your homework. Yes? And hopefully we can now get into a little bit more of the understanding of the calculations you've done based on the addition of a solute to your solvent. And then I want you thinking about what is it actually, like why does it happen? And this is going to be the hardest part of the beginning half of the semester because some of this just like is really hard to wrap your head around, and I don't even buy it, but we have really good explanations that seem to work, even though they kind of don't make sense. So we're going to get into that, and it'll be fun. And then the last part is we're going to be thinking about how these colligative properties actually matter, like why we use them, what we use them for. So osmotic pressure we'll be talking about a little bit more in class on Wednesday. We probably won't touch on it too much today, even though your primer was related to that. So for today, we're going to be focusing on boiling point, melting point changes, and how we can use that to figure out information about a compound that we don't know much about. We can put an unknown in water and see how these things change, and we can infer a lot of information about the molecule. I did mention the exam. Our first exam is going to be scheduled for next Wednesday, a week from this Wednesday. So we have today and 2 more classes. We have 30 classes throughout the semester. 3 of those are taken up by exams. And I always get the question, well, can't we have a review day before each exam? And that would not be fair to you, because that means that I would have to take another 3 days of class away, which is another week and a half of class. So we continue moving forward. Typically the day before an exam, I will do some topics that help refresh and solidify concepts that come up on the exam, but we don't stop and do any review days. The only time that has possibly ever happened is the last day of class, because finals then will be right after that. Yes?
So you did put like, I guess the exam from last semester,
Last spring's exams are posted, yes.
so like if we know how to do, I guess, all the questions on that exam, do you think they would be okay for
It's
this
a very good question. So my exams from last semesters are old exams. They are not practice exams. They are not based on what we did this semester. So there may be different things. So that semester I had students from Gen Chem 1 in the fall. Majority of my class in the spring was Gen Chem, 2 students from Gen Chem 1. So there are some things we didn't spend a lot of time reviewing, or I didn't ask the same detail, or I might have changed the approach. So use that as a way to see what types of questions I ask in the topics that we're working in. But if you're like, oh, you didn't ask any questions about this thing that we spent a full day in class doing, it's not going to be on the test. That's probably not a good conclusion to reach, right? So I want to make sure that if someone has a friend who took my class before, or somehow you're able to get my old exams, I don't want you to have an advantage, number 1. So I want everyone to be on the same playing field. 2, I want to make sure that you have an idea, just for stress and anxiety, of what types of questions I ask and how the exams are set up. So my exams don't deviate a whole lot, but I ask you usually to take concepts we've done in class and apply them to questions like I asked in class. So I'm not very often accused anymore of throwing curveballs. Being like, we've never seen anything like that before. And in my mind, when I used to teach, be like, but it's the same thing, I just like turned it around. But in class, I never turned it around. So I try to make sure that in class we actually go through all the types of ways that I can ask questions, so because that will help prepare you for the way that I think is most important, which is how I assess. So there is typically fairly good alignment between the way I teach and the way that I assess. So go through, look at those exams. They are very good practice material, but it is not a practice of the actual exam. The things that are going to be really good practice are completing the workshop activities that I give out every week, as well as you can do practice on the homework. You can do complete worksheets, go back and look at them. You can actually download them fresh from the website, so you don't have them full of notes. And then you can get together in study groups and try to figure out the types of questions that we might ask on exams. On the exam, you probably remember from the syllabus quiz that you can bring a 3x5 note card, just a regular size note card. It has to be yours. I do this as a study tool. A lot of people are like, oh, it's just a way for me to bring the information that I want, that like you think is important to the exam. So people ask me what to put on the note card. That defeats the whole purpose. I don't want me putting info on the note card. I want you thinking about, we've had 4 weeks of class, what are the most important things that we've done, and what's going to help you in class to do your best in the exam from what we've seen previously. So it is a study tool to force you to go back and kind of like prioritize what's most important. Has to be your own, has to be handwritten. I collected at the end of the exam and is shredded. So it is not something that you will be able to give to someone else. It is not something that you then use it at a later time. So it's about that process. The things that I don't allow on that note card are polyatomic ions. For this exam, the strong acids don't really matter, strong acids and bases, but polyatomic ions, if there's like a name of a polyatomic ion, you should know what that is. So if you have a list of polyatomic ions, you put that on the note card, and I consider that to be not allowed, and I'll take the note card away. So if you do not know all the names of your polyatomic ions, then it's probably worth studying this in the next exam. The exam is 75 minutes long. I'm actually not sure how I'm going to do it in this classroom. It's a little bit awkward. I'll try to figure that out. The way I really like to do it is to do like 60 minutes of regular exam. Everyone takes the exam themselves. You turn it in, and then you get to do a subset of those questions again in a group. I'll see if we have time for that this exam. But then if we do it that way, I'll talk about how that's scored. Basically, it doesn't hurt your score. It can only improve your score if your group does better than you do. And it allows you to reflect and be like, what'd you do on that question? You actually get an answer during the exam, because then you get immediate feedback on how, there are immediate feedback forms that I use, so you know immediately whether your group got it right or not. Any other questions about exam 1?
Is it paper or online?
It's paper. All of it's paper. And then me and Umi grade it. Okay. So, let's see how good y'all are at what I asked you to do in the homework, or the pre-class quiz. And as a general rule in my class, unless you are still in need of practice of finding molar masses, if I ask you something where you need a molar mass, Google it. Save time. Is there any things that you all would like that you find out that other people in your group looking up? Any values or equations? Boiling and freezing point, or
Usually you'd want that, since we're using water.
we don't need it for water. Hopefully everyone knows that. What else are you looking up though? Anyone? Anyone looking up anything else? Utilizing
1.86.
So there's a couple of equations that you might be using. I'm gonna add those up on the screen. And a couple of constants. Otherwise, it's just a number. What does it mean?
I know, but I didn't, some numbers that have to be like pulled down to zero.
Can you do that?
Yeah, if you want to hear, hold down zero. What?
That's awesome. That's very cool. Alright, so now table and see.
Oh, yeah. You know, you can like
Please include units in all your calculations and show all your calculations.
So, converting, kilograms into moles. The milliliters out.
Does everyone have a little bit of a framework to start working through this together? Or do you want another minute or two to work on your own? Do you want to work on your own for one more minute, or do you want to do it together? One more minute, and then we'll work on it together, okay?
That's the more massive round.
Did I get the wrong molar
Yeah,
mass?
Yeah, it's definitely not 300, it's like 60.
What is it?
62.
Oh, how what was it? 07. What did I look up?
I don't know, girl, but that ain't
That's the. Oh my! I looked at the boiling. That's yeah. Okay.
So if you show it when you don't need to show
And then for the mold, did you get 16.11?
Okay, let's go ahead and talk through this problem. So first off, which of the two equations am I going to use, the top left or the top right one? Why the top right? Okay, so all these little subscripts are relating to freezing or boiling, right? So we know we're going to use KF, we're going to use delta TF, we're going to use everything related to freezing. So I'm going to rewrite that down here. Delta TF, what does that mean? Delta change. Okay, so a lot of people are like, do I add it or subtract it? You have to remember that. So it's not in the equation. It's not a negative, it's not a positive. You find how much the temperature changed. And then you have to say, well, if it's freezing, does the freezing temperature always go up or always go down when you add a solute? Always goes down. So I think Ms. Katoom showed the heat curve in class on Wednesday of last week. And the thing to keep in mind is that those two, the boiling and freezing points, always get further away from each other. Maybe that helps you remember. So the freezing point always goes down, the boiling point always goes up, if you have a solution. Okay, so the change in freezing point is going to be a positive or negative for comparing it to our original freezing point. it's going to be a negative. We're going to take it away from our original value. Okay, and then it equals I times Kf for water times little m. So what is I? That's Hoff factor. It is a Dutch factor that we're going to talk about later. Okay, so for right now, we're going to say it's 1. Okay, so our Van Hoff factor is 1. We're going to spend time in class specifically digging in to what the Van Hoff factor is and how to predict it and how to use it. So for now, that's 1. Kf, what is it for this particular solution?
Negative 1.86 degrees Celsius.
It is positive 1.86 degrees Celsius. Are those the right units? What's that?
Celsius over just molality.
Okay, so one of the huge things that I try to emphasize over and over in my class in Gen Chem 1 is conversion factor. If you look at the units of a particular number, you're going to get a lot of insight, especially if it has 2 units. So let's unpack these units. Degrees Celsius over little m. What does that mean?
The temperature is going to change by 1.86 degrees per 1 every molarity, 1 mole. I don't know how to say it.
Okay, so so do a fuller sentence. Talk about it in the big picture. So the change in temperature of the freezing point, and then what you said.
It's going to change by 1.86 degrees Celsius for every 1 mole of the solid.
So if we have a 1 mole solution of anything, it doesn't matter what it is going to decrease the freezing point by 1.86 degrees Celsius. If we have a 2 mole solution, how much is the freezing point going to change? 3.72 degrees Celsius. It's going to be negative 3.72 degrees Celsius. Okay, so that set of units tells you right away that the freezing point is going to change more dramatically than the boiling point. Right? Because the change in boiling point is only 0.5 degrees Celsius for every 1 mole solution you have. So if you had a 1 mole solution of ethylene glycol, we wouldn't even have to do any calculations. You would just say, well, freezing point goes down by 1.86 degrees, boiling point goes up by 0.512 degrees Celsius, we're done. You just add it on to whatever or subtract it from the original freezing boiling point. But then the last part here is we actually need to say, well, what is the molality of this solution? And if it's not 1, we have to do some math. That's really what this equation tells us. So we are trying to find the change in freezing point and how that relates to the original. So then I'm going to rewrite the equation. Delta TF here is 1 times 1.86 degrees Celsius per every mole. And do we know what the molality is of this solution? We have to find it. So how do we find the molality of a solution? First thing, always write the units. Molality is, what are the units on the top, what are the units on the bottom?
Over kilograms of something.
I get this confused myself. If I don't write out the units for molality, molarity, percent mass, mole fraction, then I get lost too. So don't think that you're don't want to look like a beginner by writing out the units. I don't know how you would do it if you did. So if you write this out, do we know the molality of this solution? Do we know the moles of solute? Do we know the kilograms of solvent? Almost. Do we know one of them? How many kilograms of solvent do we have?
4.45.
But we don't know the number of moles of our solute. Can we find that? How do we find that? So we have 1.00 kilograms of ethylene. I'm just going to abbreviate ethylene glycol, EG. What's the molar mass?
You have to convert it to grams first and then.
Fair. What's the molar mass, sorry? 62.07 grams of ethylene glycol. is 1 mole of ethylene glycol. And what do you find numerically? Oops. How many moles is that, Samantha?
16.11.
Any questions so far on the steps that we've done? So, process-wise, we want to make sure we write out the equation, everything that we know we're going to put in, and then we figure out how to find the things that we don't know. Danielle?
Okay, so the question has two different numbers and they have different amounts of sig figs. So how do you know which one to go by whatever you're doing?
Do they? How many sig figs are there in 1.00 kilograms? 3 sig figs. How many sig figs are there in 4,450 grams? 3 sig figs. Because that 0 is only used to tell you how big it is, it's not specifically saying, I know that is a 0. It could be a 1 or it could be slightly lower. If you had a decimal there, then that would be 4 sig figs.
So why do you have 4 sig figs?
Because I wasn't paying attention. Good point.
Do you not want to wait until the very end to know the best of things?
You can, but here we would have converted it. So yeah, it's fine to keep it, but then go back and make sure you're like, because the way I wrote it, it looked like it was 4 sig figs, so Danielle had a good point. Okay, so now we know the molality. If we calculate that, that looks like about 3 point something? What does it end up being?
3.62.
3.62 mole. Alright, so what is our final answer from that calculation there? Jesse, what'd you get for the delta TF?
Negative 6.73 degrees Celsius.
I'm going to argue with you and say you probably got 6.73 degrees Celsius as your delta, your change. So you did the next step. So if you answered on an exam or someone asked you, what's the freezing point of this liquid in your radiator after we added this stuff, and you tell me it's positive 6.73, then that doesn't make any sense and that's wrong. So you will see that on my exams, multiple choice, I can't do partial credit, but on short answer, you can get yourself in a lot of trouble. So you could have done 90% of the work and found this numeric value for the change in temperature, but because the logic behind this says, I have no idea what I'm doing because I'm saying that the freezing point went up, then that would be a significant loss of credit on a short answer. Does that make sense? So to me it's important that not only can you do the math, but that you understand if your answer is wrong. And if you were to write out here, I know it's supposed to go down, I don't know what I did wrong, I would give you most of the credit for that answer then. If the numeric steps were right and you showed that you recognized something was wrong.
So when on the homeworks and everything, it would have said negative 1.86. Is there a reason you prefer just having positive 1.86?
So for me, the biggest thing is knowing which K to use and then realizing that it should go up or go down. So the logic behind that is really, really, really important. And so a lot of places you'll look and it won't have the negative or positive. So just because your book happens to have a negative or positive, don't rely on that to determine what the final answer should be. So yes, it is deliberate.
So it's
Will
like
we-
an understood negative on the 1.8?
Nope, it's not an understood negative on the 1.86. It is an understood delta TF is always going to be a change that decreases the freezing point. So the final step, did you want to add a comment?
I was just going to say, are the constants going to be on the exam?
Yes, I will give you all the constants. Good question. Because I'm not going to ask this question for water necessarily. I might ask it for another solvent. And then the KF or KB are going to depend on the solvent, not the solute. So then our final step is what is the actual freezing point? I don't know why I put that there. So we do, to answer the question itself, the freezing point of the actual solution minus, so the original minus 6.73 degrees Celsius. And so we have the final answer is negative 6.73 degrees Celsius. Okay. If we don't do that final step, and let's just say that for water, it's easier to forget that step because the freezing point is 0 and the boiling point is 100. However, if we do ethanol, the freezing point of ethanol is like minus 78 degrees Celsius. So then if you get a change that's like 5 degrees Celsius, if you give me the number 5, it's useless. You always have to compare it back to whatever the original freezing point was before you added the solvent. So how do we do on that? Do we have answers that are somewhat close to that? Negative 6.73. And then it looks like, I think Taylor showed me that you can hold down the 0 on your iClicker response. If you hold it down, then it gives you an option for a degree symbol. It's kind of interesting. So if you did want to answer the degree symbol, like Mia or Mia, it doesn't let me click them. Maybe it does, maybe it doesn't. I don't know. It won't let me click the answers. But you can add a degree symbol if you'd like. But just putting 6.73 as your answer too would be completely and utterly useless. Is it Kelvin? Is it Fahrenheit? What is it? You have to tell me that you understand that that is a change in temperature from the natural freezing point of that solvent. Okay, so I am very process oriented, but I'm also logic oriented. So if you don't show me you understand what you're doing, it's hard for me to say that you get full credit for completing a question. All right, so let's do the boiling point. Y'all can do this on your own this time around. And I want you, as you do this, to think about the sentences you'd use to describe how your calculations are used to make sense. Let's do about 3 minutes of this calculation. You guys should be done. It's not like a forced touch, it's just like pulling it up. Which helping all of us get smarter.
Well, that'll be the, the change, the way that the
Okay, so constant is different, and then the final. Before it's freezing point of water, after freezing everything after freezing, you can compare that change to where it's normally. So before it's 0 degrees, we made it lower. Now,
I expect to get through it pretty quick. That's like 14 questions, last 3 questions.
Fahrenheit body. Alright, we got 21 responses. We're almost 3 minutes in.
It's already came out.
Can I get someone from this table to volunteer the process we used? And I can write it up.
It's just the same thing.
Same thing, but what's different?
The K values, you use the 0.512 degrees Celsius per molal instead of the other.
Okay, so we're going to use the same Van Hoff factor because I said so. We're going to use our KB in this case, 0.512 degrees Celsius per molal. And then what was our molality? 3.62
Oh, yeah.
mole. Okay, and when you write this out, let's just pretend at all times that I'm going to be there grading it on an exam. I will absolutely look for this. So these units will cancel out. If you don't write the units, then you might put molarity here. And if you calculate molarity, then that's not going to work because this is based off of concentration and molality.
Do we have to write it necessarily like that? Or is it just as long as you have the units?
You have to include units and you have to show it in a way that makes sense. I'm not quite sure how else you show it, but if you do another logical way, that's great. Okay, and so what's our final answer here? Cat. Oh, sorry, Amber? $1.85. Okay, so I'm going to submit this answer. We're done, right? Okay, so then we have no idea what the context is. So what do I need to do to get the final answer?
We add it to 100 degrees.
Okay. And what's interesting is we're never going to use the boiling point as our limiting sig figs. So I said 100 degrees Celsius is the boiling point of water. I'm not going to use 100.00 or 0.00000 or whatever it is. So we're going to make sure we use the sig figs from our calculations to limit. Because we could go somewhere and we could look up a much more accurate version of exactly what this is. And actually this changes based on pressure. So there's a lot more to it. So always use appropriate sig figs for your calculations. And if we're comparing that to a literature value, assume we can always go look up a more accurate version of that literature value. So, based on sig fig rules. By the way, if you don't remember sig fig rules, figure them out before the first exam, because I will say that people typically use about 2 to 3% on an exam by not remembering sig fig rules, because every single question that has calculations, I do assume that you were taught and know how to use sig figs. So if you don't know how to use them, and that didn't make any sense to you, how 100 plus 1.85 gives you 5 digits, then come see me, and I'll help you figure it out, okay? Or you can work on your own to do that as well. All right, any questions on how we did that? What would change if I did another solvent? What's that, Danielle?
Did the modality change?
It depends. If it was 1 kilogram of, if it was the same mass of the solvent, then no, molality would stay the same.
Your K values?
Our K values, these are specific for the solvent. Doesn't matter what the solute is, these values are what dictate it, because we're changing the freezing or boiling point of the solvent. So Kb or Kf are specific to any specific solvent. What else might change? Anything else?
Would it be the freezing and the boiling?
Yeah, the freezing and boiling point would be different starting points that we would then calculate the change from. Great. In my slides that I'll post tonight, these slides, I have hidden how to work through those as well. So if you didn't quite follow what we're doing, you can go back and look through that. I always try to think about it process-wise and not memorization of like steps. So that's why I don't show you like the fully worked out maps, but you can go back and use that if you think that'll help. So I want you to take about 30 or 45 seconds, and on your own, I want you to think about the answer to this question. Why does the boiling point always go up when you add a solute? When you dissolve a solute, I should say. Why does it always go up? So think about that on your own for 30 seconds. On your own. And then you have a couple ideas, then discuss those in your group. And I'll ask for some ideas to be shared out. Think about the molecular review. What's happening? bonds means covalent bonds. We're not doing that. That's well. And that's not what we're talking about. Okay, I'm gonna pick on the screw this time. What are some ideas of why the boiling point always goes up when you add solute?
You've got more intermolecular forces to overcome in order for molecules with phase 2 to escape.
Okay, so it's going to take more heat, more energy in order to overcome those interactions between molecules. Okay, what other ideas do we have? Additional ideas. Add to that. Jesse?
That's all I was thinking.
There's another one that I heard. I can't remember where I heard it.
I'll just say this, I don't know if it's right, but I said it's because more particles are added, I don't know if that is the right word. But
So,
with the amount,
Can you elaborate?
no.
So why are you saying particles? What's
I don't know, I think I heard that somewhere. I don't know why.
Well, because I think what she's trying to say is like you're adding a solute to the solvent, so like there's more of a like the solution is larger now because there's two things added together.
okay?
Instead of just like if water was by itself, like when we add the solute, obviously it gets like
There's now more mass.
yes.
And there are more things there. This is true.
I tried. I'm sorry.
Um,
Go away.
But one of the discussions I had was around that means that it might take more heat to get to the same temperature, but then it should still boil at 100 degrees Celsius if there's no other justification, right? So I think by adding mass, it wouldn't necessarily change the boiling point. It would just take more heat to get to the boiling point. But we're saying 100 degrees Celsius is no longer the boiling point of water. So the most logical explanation is what Michael said, what a lot of people said, is that you add a solute to solvent and you have more pull between the molecules, which means you need more energy to overcome it and become a gas, right? To boil. Turns out it's wrong. It doesn't matter what the solute is. So check it out. You can have a sodium ion. We'll talk about Van Hoff factor in a second, how that plays in here. You take a sodium ion, maybe let's say one sodium chloride, right? One sodium ion, one chloride ion. Those are dissolved in water. Those would have the same impact on boiling point as if you had a protein. So sodium chloride has one positive ion, one negative ion. A protein, so they weigh together for about like 50 daltons, 50 grams per mole for sodium chloride. You can add one protein that has 1,000 atoms in it, and it has 500 polar bonds in it, and the sodium chloride would have a stronger impact than that one protein. Even though that one protein had so many different IMS that it's having with all the different things in water, the sodium chloride would have twice as much of an impact as the protein. So it turns out that the two questions are, one, does it dissolve? That's why when a solute dissolves is really important. If a solute doesn't dissolve, then we're not even talking about any of this because you don't have a solution. In order to have a solution, something has to dissolve. So yes, it has to be polar to dissolve in water, and if it's ionic, it almost always dissolves. Okay? So yes, it'll go into water. But then the second question is, using the term that Alexandria
Yes.
used, is how many particles are there in solution? Those are the only two questions that matter. That's it. How many particles are there, and does it dissolve or not? If it doesn't dissolve, we don't care. If it does dissolve, then we get 2 particles, or 3 particles, or 4 particles for every one. That's going to have a much bigger impact. So the only logical way that I've heard, and so here's where this really doesn't sit well with me. Experimental data supports this over and over and over and again. So we have to have some sort of idea. Why does this happen? Some sort of explanation. And the best one that I've heard, it's not great, but the best one I've heard is this idea that we have the surface, let's say the surface of a beaker, or something like that. And at the surface of this beaker, we have a lot of water molecules. And if we have only water molecules, then whenever a water molecule comes to the surface and is moving fast enough to overcome the intermolecular forces, it gets a chance to go and become a gas. But if there is something else there that is not water, and that actually is non-volatile, which means that it doesn't evaporate at the same temperature, so sodium chloride, right? Table salt doesn't evaporate if you put it at 100 degrees. If you add, let's see what color is going to be good. Purple. Can you see those dots different? You can't really see those dots differently, can you? Let's do red. So if 5% of the entire molecules in that solution are something that doesn't dissolve and water runs into that on its way up to the surface, what's going to happen to it? It's going to bounce off and it's going to come back in. It is not going to be allowed to both have the speed and get to the surface unhindered to be able to be released from the IMFs as a gas. That's the only logical explanation I can come up with, or that I've heard, and I've asked a lot of people about this. It is literally about what percentage of the surface's molecules are a solute. Does that not sound logical? It doesn't sound logical, right?
Like, I don't even know how I would write that on my paper right now.
What's that? It literally is blocking. It's what percentage of the surface are going to be waters. And if it's you run into one that's not the water, you're going to be blocked.
So you just,
The oil is gonna always increase because
Sorry, 2 statements at once. Go ahead.
Instead of thinking that you have a beaker of solution, you have to turn that into essentially a surface of this.
The beaker of water is all molecules moving different speeds, but the only place that they can become a gas, unless you're like superheating the bottom, is at the surface. So that percentage of the surface that is blockers is what matters. And the higher the percentage is, the more blocking you're going to have. It does matter what the solvent is, right? Because the stronger the IMFs are between the solvent molecules themselves, the bigger difference there's going to be in KB. So KB is where that calculation comes into effect. But then how that actually plays out seems to be based off of that blocking effect. It hurts my head. And if anyone can come up with a better description or definition of why and do your own research, I would love to know it because I've been looking for a long time. And I feel like I know a little bit about chemistry, but this is the best definition, this is the best description that I've been able to come across.
So you could write it in a sentence that says the boiling point always increases because.
That's a good thing you should try to write down. Does anyone else want to try? Do you want to try?
Because the solutes preventing the solvent from, wait, backwards that, breaking free from the.
Yeah, be careful, because if you say it's preventing from breaking free, it could just be it's holding on to it. It's just like it's more attracted to it, and it doesn't matter what the identity of it is. The identity, as long as the identity says it dissolves, then the identity is irrelevant after that.
It's like,
It doesn't matter to talk about other particles that have a higher boiling point?
Yeah, or that are not volatile is the other way to say that. So if your solute is like ether, something that you just like boils at room temperature, then this is a bit of a different effect. But if it's a solute that doesn't evaporate until after water evaporates, then this effect is true. What about the freezing point? Why does the freezing point always go down?
Would it be the same?
So it is also irrelevant what the identity of the solute is, as long as the solute dissolves. So then why does the solute lower the freezing point? Boiling point's at the surface. Is the freezing point just at the surface though?
The particles interfering with the lattice structure when they slow down in order to slow it down.
So in order for a compound to go from a liquid to a solid, you have to have them slow down enough where now those intermolecular forces are kind of locking and forming a lattice, a crystal lattice. But if there's little particles in between it, then it's going to have a harder time. It's going to have to be going even slower to line up appropriately to get those lattice structures. So let's do a couple questions about the Van Hoff factor, since I promised we'd get into that. So this is question 7? 6. Question number 6. Go ahead and answer this. Read through it.
You don't remember? I don't know. Sorry,
What's
my
up?
brain is, I'm like, that messed my brain up for a second, okay?
Oh, it still messes my brain up.
The
still just
freezing
stuck on the
point always
freezing.
decreases because what? The lattice structure?
Yeah, so you know when things slow down and they form a solid, there's like a really organized structure. So if you have little things in the way, then it's like harder. It has to be in an even more specific place for it to freeze.
So it like messes up the lattice structure.
Yeah.
Kind of like locks it into place.
Other way around. It makes it harder to lock into place. Because particles need to be moving even slower in order to form that lattice.
The Van Hoff factor.
Alright, let's do another 45 seconds.
Is it
What's that?
Yeah, it makes a lot of sense when you look at that, the equation for it up there, because you just multiply.
Talk amongst your group. Alright, 10 more seconds. Lows and out, take your best guess. Is it 1, 2, or 3, or are all of them the same? We're closing out. So we do have a bit of a mix on this one. Why is answer A the best answer for this? Talk amongst your tables. That was not the majority answer. Talk amongst your tables. Why is solution 1 going to have the lowest freezing point? What's that? Who's your turn? Okay, so who has a sentence they think describes why solution 1 is going to make the lowest freezing point?
Because it's got more iron.
Okay, can we have more of a sentence then? Can we build off of that? Make more?
And the more it has.
Okay, so I'm going to kind of pull this together with what we talked about before. So we said it doesn't matter what the thing is. As long as it dissolves, then it's going to impact the freezing point. And then the second part of that is how many particles are there? So we said each one of these we're going to dissolve the same number of moles of that compound in water. What happens to calcium chloride when it dissolves in water? It forms 1 calcium ion, 2 chloride ions. It forms 3 total ions. That's called the Van Hoff factor. So the Van Hoff factor is 3 for calcium chloride. What is it for sodium chloride? 2. And ethanol? Any molecular compound, anything that does not have ionic bonds, has a Van Hoff factor of 1. Which is why ethylene glycol has a Van Hoff factor of 1, because it's only carbon, hydrogen, oxygen bonds. There are no ionic bonds in that molecule, so the Van Hoff factor is 1. So really what we're saying is that solution 1 ends up with 0.75 moles of particles in solution. Solution 2 has 0.50 moles of particles in solution, and solution 3 is only 0.25 moles of particles in solution. So that is a theoretical Van Hoff factor. So if you look at that next table, I show the theoretical Van Hoff factor for a lot of these different compounds. If you look at these and you don't know the names, that should be an indicator you probably need to study polyatomic ions. But for the top one, we have 4 different particles, 3 sodiums, 1 phosphate. Potassium, it's 2 potassiums and 1 sulfate. We kind of go down the list. And so if you look at, this is theoretical. But as many of you know, theories only get us so far. So we can test it. We can take a mole of sodium phosphate and put it in water and see what happens. And while we think that there should be 4 particles for every 1 sodium phosphate, what we find is that in reality, we only have about 3 on average, between 3 and 4. So that means that not all of the sodium phosphates actually break apart completely. That they break apart, but only partially, because water has to surround each one of those ions. Potassium sulfate, the actual Van Hoff factor, the experimental, when you go measure it in the lab, is also lower. Calcium chloride, it's a little bit closer. Magnesium sulfate is pretty terrible, so that means it doesn't dissolve very well at all. Sodium chloride is decent. So does this remind you of our solubility charts from Gen Chem 1? Thinking about, does the salt dissolve or not? This is what it's talking about. Is there's different levels of it dissolving or not. And later this semester we're going to spend a lot of time talking about actual calculations of how much something dissolves or not. But this gets us some insight. So, last thing I want to show before we leave class. 2 things. 1, ethylene glycol dissolves. It does not split into carbons, hydrogens, and oxygens. So this little diagram is from Facebook. It's a guy called a bumbling biochemist. He made this diagram, this little cartoon. We're talking about, does it dissolve, firstly, and secondly, if it does it also break up, does it disassociate? And those are not the same thing. So before you leave, make sure you look at the learning objectives for today. Think about what I should and should not be able to do. And, last thing, very important. Workshop this week. We will have workshop tomorrow, but Wednesday is the Friends of Science and Medicine seminar series, and I would love for everyone to go to that. So that starts at 4:30, and it is in Physics 101. So we will only have 1 workshop session this week. It is going to be extremely important that everyone completes that packet, though, by the time we're done with Exam 1. It's starting us on kinetics, which is going to be something we start on what is it, the 22nd or whatever that following Monday is after Exam 1. So if you don't get a chance to go tomorrow or come to office hours this week, I really need everyone to work on activity 36. And if you have the other activities you want to show them to me that you've completed them, go ahead and let me know so you get credit.
What is
If you did not go.
What is the Friends thing, science?